Okay, good evening, ladies and gentlemen, and welcome to our public evening lecture here with regards to Umjikelezo We Science. My name is Tanya Reinhardt, and I'm the Science Center Coordinator at the University of KwaZulu-Natal. And today I am going to talk to you about diamonds and, and give you some more background information about those ones here. I'm going to start sharing my screen again. Okay, so the title is Diamonds, Not Just a Pretty Mineral. Again, I'm Tanya Reinhardt, and I'm the Science Center Coordinator at the University of KwaZulu-Natal. So this project, in fact, has been funded by the Department of Science and Innovation, NRF SASTA, and it is part of our Umjikelezo We Science outreach activity, which is a consortium of different organizations, the Center for the Advancement of Science and Mathematics Education, KZN, the Durham Natural Science Museum, the KZN Science Center, Kitchen Chemistry, the University of KwaZulu-Natal, and the UniZulu Science Center. Okay, so let's just dive straight into the topic. Okay, so this is a picture that's been taken in 1873, which depicts the first, or not really the first one, but the new rush. So this is when basically the main diamond rush on sorry, I'll just have to hide my video panel. The main diamond rush on Kimberley started. And what is it actually that attracts people to this? This also might look familiar. So this is a picture that's been taken fairly recently, and this is the headline for it. Diamond rush hits tiny KZN, hundreds flock to KZN village over diamond rush. And sadly though, unfortunately, no diamonds. So what those people picked up were just ordinary quartz crystals, not really as much worth as diamonds. But what is it that makes diamonds so special? Why do people write poems about diamonds? You are my diamond, and my diamond you shall be. Diamonds are forever, and so are you for me. Diamonds are delicate as can be, and you are as sweet as can be. So people write poems about diamonds. People make films about diamonds. Famous James Bond, Diamonds Are Forever, or Blood Diamonds with Leonardo DiCaprio, or Diamonds Were Forever, which is another film that was screening. Diamonds also seem to inspire music, and I'm just gonna play this one here.
A kiss on the hand may be quite continental, but diamonds are a girl's best friend.
So the famous song by Marilyn Monroe, or if we're going to go a little bit more modern.
Shine bright like a diamond. Shine bright like a diamond.
Or if we want to really go the other route, we have this one.
Lucy in the sky with diamonds. Lucy in the sky with diamonds.
And there is, in fact, a white dwarf with a diamond core nicknamed after the song. So this is Lucy, and it has a diamond core, and it's probably the largest diamond currently here in our universe, so that we know of. So what is this magical substance called diamond? Quite frankly, it is just simple carbon. So very simple carbon, and you can get carbon as a diamond, and you can get carbon like this as graphite. And if you don't know what graphite is, when you look at your pencil, so the pencil tip is basically pure graphite. So you can see both are made out of carbon. So what makes them different? The difference is that they are in fact different, what we call crystal structures. So here your diamond, in the diamond, your carbon is surrounded by 4 atoms, and they form what they call a tetrahedron. In graphite, your diamond is in a form of a ring, a hexagonal ring, And these rings are connected to form sheets. And these sheets are in fact glide easily past each other. And this is, why graphite is so soft. And here you have in diamond, you have very strong bonds. So this is why diamond is very hard. And diamond is in fact one of 3 natural modifications. Graphite is one of the other ones, or allotropes of carbon. Diamond is also currently the hardest mineral on Earth. So it's 58 times harder than anything else that we know currently in nature. So how do diamonds form? So when we are looking at diamonds, we need high temperatures and high pressure. And here at the bottom right, what you see here is in fact the diamond stability field, or the stability field of diamond and graphite. And in order to get diamonds, if we follow what we call the continental geotherm, so what it basically means is the deeper you get, the more pressure your rock is going to experience. And also you can see there is an increase in temperature. So in order for a diamond to get formed in continental terms, we actually have to go down fairly deep, down to about at least 160 kilometers. And quite high temperatures. And this is the area where, in fact, diamonds form. So here we have different scenarios of how we can actually achieve, or how we can get diamonds. So we can have micro diamonds, tiny little nano-sized diamonds that we can find in meteorites. So during meteorite falls, we can actually get diamonds from outer space. We can have diamonds that are formed through impact. So if we have, for example, a graphite bearing rock, and the graphite bearing rock gets hit by a meteorite, the shock wave might produce enough pressure, enough heat, enough energy to convert your graphite into diamond. Then we can also get diamonds that's been transported down to the subduction zone. Diamonds and then are basically transformed into diamonds and then come up through other geological processes back onto the surface of the Earth. But for us and for South Africa, the most important diamond source actually comes from within the mantle due to some form of volcanic eruption. And last but not least, we can get these kinds of diamonds, synthetic diamonds that can be made in laboratory, in labs under specific circumstances. So let's start a little bit to look at more the natural occurring and quite possible kind of diamonds here in South Africa, our primary deposits. So what we have here is we have diamond-bearing pipes, so-called kimberlites. Remember, they originate from very, very deep down. So they form at depths of about 160 kilometers and below. And you remember the reasons for it. Then we are basically in the diamond stability field. And then they finally erupt violently and rapidly and bringing the diamond up to the surface. Only 1 in 200 kimberlite pipes actually contain gem quality diamonds. And the rock kimberlite is in fact named after the town of Kimberley. So let's have a quick look at some exploration. So here we have a distribution of the kimberlites worldwide. So you can see that Southern Africa has quite a large number of kimberlites, and especially in Southern Africa, so in Botswana and also in South Africa and also in Namibia. So here we have large diamond, so minor primary deposits, but also major kimberlite deposits. And you can see that the majority of these major primary deposits are in fact on old continents, so-called cratons. And then we get also so-called secondary deposits. So these ones are basically when your kimberlite erodes, and kimberlite is a rock that erodes. It weathers quite easily, so it weathers, it breaks down, and is then eroded and transported, usually along rivers, riverbeds, and you can find quite a lot of diamonds actually in specific areas, for example, the Orange River. So how can we in fact know, how do we know, how can we find diamonds? How do we know that we actually close on finding diamonds in kimberlites? So what scientists look out for are so-called indicator minerals. So these ones are minerals like garnet, specific types of garnets with a very specific chemical composition. There are something that are called diopsides, chrome diopsides. So these ones are very important indicator minerals that come up with specific types of rocks that are usually associated with diamonds. We also have chromite, we have olivine, we have zircon, and we have ilmenite. So these ones are the kind of minerals that prospectors or exploration geologists are looking for. So how does it work? So usually you will earmark an area where you would like to look for these kinds of diamonds. You would send out a team and they would look at, for example, gravel riverbeds and things like this. They would take samples, they would analyze these samples. And if they have kind of a good accumulation of these types of minerals, they would basically then start evaluating the associated kimberlite with it or the associated deposit with it. So, talking about deposits, so what kind of deposits do we know? So remember, our diamond deposits usually consist of your primary kimberlites and your your primary deposits, which are your kimberlites, and your secondary deposits, which are your alluvial deposits. Remember those of the broken down kimberlites that's been transported. And here is a little bit more a detailed distribution of your primary kimberlites here in Southern Africa. So here we have simple kimberlites and the red ones. So these ones are the green ones, and you can see quite nicely around Kimberley, we have a huge number of these kinds of kimberlites, also up in Lesotho. There's a little bit here in KZN as well. But they are just kimberlites, not diamond-bearing kimberlites. We also have the red ones. These ones are basically the kimberlites that have been mined for, in fact, the diamonds here. Again, the majority here in around Kimberley, but also around Pretoria, so north of Johannesburg. And then we have, remember I was speaking about, talking about the alluvial diamond deposits. So, so these ones are basically deposits now along the main rivers where, you know, remember your kimberlite got weathered, eroded, and the diamonds were transported along these rivers and deposited along these rivers. So we have old alluvials, but also we have recent alluvials, and quite interesting, we also find diamonds basically offshore in the Atlantic Ocean. So these ones are basically the kind of deposits that we know here from Southern Africa. So remember your alluvial, we have open pit mining, we have underground mining, and we have marine deposits or marine explorations. So the most common type or most common method of recovering diamonds is in fact the open pit mine. And here we have a nice example with a photo in the background where you can see the, let's say, diamond mine in Lesotho. And these ones, or this kind of method is basically used when the diamonds appear near the surface. So what happens is they usually blast the rocks, so they break up the rocks before it's been processed. They're taken then with a truck to the sorting house, where they might be further crushed and then basically extracted from the rock. A more technical, complex way to extract diamond is the underground mining. It's a huge, complicated process where you drill basically boreholes in the roof of the mine. You set explosive there, and then you explode or try to shatter the rocks above, and you basically try to extract the diamonds from within it. So this only applies if the open pit mine is uneconomic. So if you have to remove too much of source rock, or if your diamond bearing rocks are fairly deep down. So this is only viable if you have high quality diamonds deep down. So otherwise it's highly uneconomical an uneconomical extraction method. So an example of this one is basically the Kellerman diamond mine here in South Africa. Alluvial is the oldest diamond mining method. So here, remember, your diamonds have been carried away by wind and water down the rivers over millions and millions of years. And so what happens is they just basically dig up all the sand and gravel. They sort it through. Sometimes they have to also, break them a little bit down. I once visited an alluvial diamond mine, and the regulations are very strict. You weren't allowed to bend, you weren't allowed to shuffle with your feet, and it was quite something. And not that I ever got to see one there, but these ones are basically the regulations there. So here we have an example. This is the Saxondrift diamond mine here in South Africa. And as I mentioned, there are also diamond deposits offshore in the Atlantic Ocean off the coast of Namibia. And here the sediments are dredged from the ocean floor. So you just have to imagine that they have some kind of, I don't know, vacuum cleaner or whatever, and it goes down to the ocean floor. And there the sediments are being brought up onto the ship where they're crushed and the diamonds are extracted. And this is the MV Mafuta, which is based just before Namibia, the Namibian coast. So again, let's have a look at the economic side of diamonds. So the sorting site. So what we have is, of course, the rough diamond classification. Not every diamond is kind of valuable, or can be used for jewelries. So what is the lowest type of diamond that you can get? That is the so-called board. This is the worst quality, and this is usually used for, as dust for diamond polishing. So where would you use it? For example, when you look at, if you have a fancy kitchen and you have granite in your kitchen and you have these shiny surfaces or rock surfaces, that's been usually done by through diamond paste polishing. Then we have the industrial diamonds. So these ones are smaller or lower quality diamonds. And here, what they used for is as small bits and pieces. They're going to be implemented in an alloy. And so these ones here you have for drilling and cutting tools. So if it says it has a diamond blade, don't expect that it's a complete blade made out of diamonds, but they just have some small industrial lower quality diamonds in it, embedded in some alloy, which is still pretty good, and it's still fully sufficient. And then, of course, we have our gems. So here, again, not every gem is like the other one. So not every gem quality diamond is like the other one. So we have different classifications. We classify them according to size, according to shape, according to color, and of course, according to quality. And once everybody is satisfied, people turn them into the most astonishing and most beautiful jewelry, of course, and of course quite expensive jewelry. And here, what we have here is probably one of the most luckiest experience that I ever had. I was very fortunate, or we were very fortunate to visit the Litseng diamond mines, the highest diamond mine in the world in Lesotho. And we were actually allowed to see a monthly production. And this is just half the table, so you have to imagine that the other half is just to the left. And here you can see these ones are diamonds, classified, sorted diamonds. So here we have diamonds that are about 10 carat. So here we have slightly smaller ones, and you can see they come in all sorts of different kind of colors and shapes and sizes. And this is in fact my hand here, and I'm holding a diamond, and it's exactly this diamond here, which is probably roughly about 70 to 80 carat diamond. And we were absolutely fortunate to see this diamond. The reason was because they previously found another big diamond that they usually fly out. So, and because they've already flown out one, this one was still there. So, I mean, this is like, you know, winning the lotto, or, you know, have a zero and at a table of roulette or something like this. So it was quite extraordinary. And I was holding this diamond in my hand. And when I looked at this diamond, I suddenly kind of got to hear some kind of whispering coming from this diamond. So I put it closer to my ear. And can you imagine what it said? Take me, take me. So I looked at the diamond, and then I looked at the guy with the machine gun that was standing right next to the door. And then I decided, no, sorry, maybe another time, or maybe I can ask my husband to buy me these kinds of diamonds or these kinds of jewelry. But I had to unfortunately leave it there. So, of course, everybody is keen to know, you know, what determines the price of gem diamonds? And here we have the classic 4 C's. But before I'm going to tell you a little bit more about the 4 C's, is in fact the reason why diamonds are so valuable. It is not because they are so rare. They are not. And it's not because, you know, they are so precious gemstones. It is simply one of the most clever marketing strategies that De Beers initiated in 1947. And this slogan still sticks. A diamond is forever. So it appeals to, you know, if you want to buy something precious, you know, for your loved one, the one that you want, you have to buy a diamond, because a diamond is forever, and it still sticks. How can you make 2 months' salary last forever? So here is a continuation of this very famous advert that was initiated at that point. So diamonds are not really that rare, as I said, and if, you know, all the diamond resources in the world would be thrown onto the market, you would actually get fairly cheap diamonds. Also, diamond is sometimes not really the most expensive gemstone. So there are other gemstones. So for example, if you, for a quality ruby, you pay way more, sometimes way more than for a diamond. So, but let's go back to the 4 C's that in fact determine the price of a diamond. So first of all, we have a cut, or the cut. So if you look at the cut, and it's very important in order to bring out the brilliance of a diamond, is it needs to have an expert cut. So you can have the most magnificent, flawless diamond, but if you have a crappy person or a crappy cutter, then you're basically reducing the price. And here you can see the 5 classifications. So, and this all depends on the internal reflection of the light ray, so that you get this very, very nice sparkle. So if you cut too shallow, you only have like very poor reflection. Shallow still gives you a little bit of a sparkle. Ideally, you get this full bright color that the diamonds are famous for. Again, with a poor cut, a lot of the reflection basically is not going to come out through the front, so through the top here, but it's somehow disappears at the bottom of the diamond. And then if you have a very deep diamond, it's actually very poor cut. Again, this determines the cost. Then, of course, the color. So usually, you know, diamonds are colorless. Sometimes they have this bluish tint, which are a little bit more expensive than your yellowish tint diamonds. But nowadays also, we have something that's called fancy diamonds, where these diamonds, in fact, have some really nice colors. And so you get nice blue colors, and this is because of boron incorporated in the lattice or crystal structure of the diamond. You can get diamonds that have been exposed to gamma rays, and you get a nice green color. The yellow color of a diamond is because of nitrogen incorporated in the crystal structure. A violet color diamond you get if you have hydrogen incorporated in the structure, and you get shades from purple over red to kind of orange. This is when your lattice, your crystal structure of your diamond is slightly deformed. So again, fancy diamonds, beautiful colors. I know that, for example, the Argyle mine in Australia produces very nice kind of purplish reddish colored diamonds. And then, of course, the weight plays a significant role. So if you only have like a 0.02 carat diamond compared to a 6 carat diamond, you will, of course, pay more for a 6 carat diamond. So the carat, or the terminology carat, originates, in fact, from the carob seed that people used in the past to weigh, to have a kind of a precise correlation between the diamond itself and the amount of carob seeds. Later on, they figured out that the carob seeds actually weigh different or have different weights. So nowadays, 1 carat is 200 milligrams. And so you can now kind of calculate how much, for example, a 6 carat diamond would weigh, or the 70, 80 carat diamond that I was showing you earlier on. And then, of course, we have the clarity. So how flawless is a diamond? And again, for jewels, you want something that is flawless, so free of all inclusions and blemishes. And this is what you have to look under a 10 times magnification. And here you can also see the kind of grading for it, and you get very, very slight inclusions, so they are difficult to see under a 10 times magnification. You get very slight inclusions, so you can slightly visible under a 10 times magnification. You get slight inclusions visible under 10 times magnification, and then you can get inclusions that are visible to the naked eye. But what the diamond industry classifies as a flaw, it is actually quite important for the scientific world. The scientific world, scientists see this as an opportunity. And this is an opportunity to have, to basically look inside, to open a door inside the interior of the earth. And this is the opportunity. So coming up with diamonds are minerals that originate from within the earth. So from the upper mantle, from the lower mantles, even sometimes. So we get inclusions, for example, of olivine, garnet, chromite, sulfide, coesite, some very strange names, valstromite, ringwoodite, ferropericlases, jeffbenite, and different kinds of garnets. And these inclusions that come up with these diamonds tell us something about the interior of the earth. So it is quite important, in fact, that we have a look at these inclusions, that we basically analyze, or that scientists analyze these inclusions. So what do they tell us? So first of all, they tell us something about the mineral composition of the earth itself, and all the things that are coming up with. It's not only like mineral inclusions that are coming up, but also some fluids that are coming up. So it tells us also something about the chemical composition. So regard diamonds as a kind of a vault or a safe that you where you put something in, and then you ship it and transport it over very long distances. And when you open it, you still can see, or you can look inside the safe, and you can still see what's been inside. So again, it provides us an insight into the interior of the earth. So in here we have some very strange and very famous examples. Remember, we have drilling, so where we drill drilling projects, where we drill into the interior of the, or try to drill into the interior of the earth. The largest man-made drilling project has been done in Russia, and they drilled up to the depth of, believe it or not, 12 kilometers. So this is just barely scratching this crust. So it doesn't even go down into the upper mantle, it doesn't even go down into the transition zones, doesn't even go down into the lower mantle. So drilling only gets us so far, but for example, looking at these diamonds and what they're bringing up, what kind of minerals they're bringing up, tells us way more about it. A lot of things that we know about the mineral compositions and what kind of minerals to be expected inside, for example, in the lower mantle and transition zones, have been done through experiments. So scientists basically made experiments, and they have a good understanding of what kind of crystals or what kind of minerals to expect. And one of these minerals is, for example, the ringwoodite. Known previously only from meteorites, ringwoodite was actually coming up with a diamond, and you can see this beautiful, beautiful blue color. Also, ringwoodite has been synthesized in labs, and again, a fantastic, nice blue color that was coming up for it. And the ringwoodite, as you can see, comes up from the lower transition zone up with so about 500, just below 520 kilometers. And this indicates, the analysis also indicates that there is some form of water in the transition zone. How the water, please don't ask me how the water is going to look like down there. So it just indicates that there is water down there. And then last year, scientists got very, very, very excited because they basically found a mineral, and this is one of the three main minerals in the lower mantle, coming up with a diamond onto the surface. Because it's such a strange mineral, they would never have expected to see it actually on the surface of the earth. But here it was, trapped inside a diamond. This is a mineral called, and it's got this very strange name, a Dave Mauite. Again, this is one of the three main minerals in the lower mantle. It makes out of about 5 to 7% in the lower mantle. So, but What about the most abandoned mineral on Earth? And sorry, guys, I have to disappoint you. We don't find the most abandoned mineral here on the surface of the Earth, not in the crust. We find it down in the lower mantle. And this is a mineral called bitumenite. It basically has 38 volume percent, or takes 38 volume percent of the entire Earth. Can you imagine? And we only know it because people have seen it in a meteorite sample that's been brought from outer space, but they haven't seen it as it in its terrestrial form. So again, just to come back to the Dave Meyer White, so this mineral basically comes from the lower mantle. So that means from below 660 kilometers down. So can you imagine? So now we can look inside the Earth. We can see a mineral that's been formed at 660 kilometers depth at least. So I think that's really quite exciting. And maybe one day, maybe we even find one of these ones here, one of the bitumenites in one of these diamonds. Also, the inclusions also tell us something about more. They tell us something about the age of the diamonds. Diamonds, unfortunately, themselves cannot be dated. I mean, you can say, hello, diamond, I want to date you, or you can date the owner of a diamond. But diamonds itself, because they consist of carbon, and carbon only has a very short half-life in geological terms. So diamonds are usually old, fairly old. So carbon dating is unfortunately not an option to date diamonds. So what they basically do is they look at mineral inclusions in these diamonds and basically determine the age of the mineral inclusions, and then determine therefore from that the age of the diamond. So for example, here in South Africa, the Cullinan Venetia diamonds are around about 2 billion years old. So very, very old. Whereas here we also have very young diamonds. So the Jagersfontein and Koffiefontein diamonds are only 90 million years old. And just to finish off, the question is, does the slogan, "A diamond is forever," still holds? And you can see this joke here. Your dad said it's been under a lot of pressure lately. Ladies and gentlemen, believe it or not, you can convert your loved ones, be it a dog, be it a husband or a wife, a spouse. You can actually convert your beloved ones into a diamond. So these ones are here. I'm not getting paid for this, but these ones are just an example of companies that in fact convert, for example, the ashes of cats, dogs, and relatives into diamonds, and you can keep them. And then you can say, oh, okay, so here we have, this is my first husband, this is my second husband, this is my third husband. And with that, I'm finished. Thank you very much for your attention. And I just wanted to find out, are there any questions that you want to ask? Then please unmute yourself.
Yes, good evening, Tanya.
Hi, Malinga, how are you?
I'm good, and yourself, how are you?
I'm very well, thank you. Yes,
Yeah,
Malinga, what is your question?
Sure. Thank you for your wonderful presentation. I just wanted to check with you. You know, last year we had a saga in Ladysmith where we had a lot of people traveling to actually dig up the so-called diamonds. What was the story there, and what was it that they were digging up?
Okay, so I just mentioned it a little bit earlier on. This was basically our very own recent diamond rush. And so what people believed was diamonds was in fact no diamonds. They were just simple quartz crystals. And the problem, of course, is to tell to those people, sorry guys, you did not dig up a diamond. It's just ordinary silicon dioxide, and so they usually don't believe you. So because they think that you want it for yourself. So this is basically how things got a little bit out of hand. But I think in the end, they've been told, unfortunately, no. Sorry, guys, those ones are not diamonds. Those ones is in fact just simple quartz. And this is what they digged up. I can show you a photo. Let me just, sorry, just go, if I'm going to go back. Show you just the photo. Oops. So here you can see, can you, here you can see, so this is basically, this is the very typical quartz form that you see here. What people can try out, of course, is if it scratches glass or not. So usually quartz has got the similar hardness of glass, so it does not scratch glass very easily, whereas diamond would scratch glass easily.
Oh, okay. No, thank you, Tanya.
Okay, right, Cern, you had a question as well.
Hi, good evening. Thank you again for that. Can you hear me?
Yes, I can hear you, Cern.
Great. Yeah, no, that was a fantastic, shiny book. Thank you again for that. I got a crazy question. There was just two things I just thought of, as crazy as it might sound. I mean, I'll quote a Pink Floyd song called "Shine On You Crazy Diamond." So I'm going to be a little crazy when I ask this question. It's just a thought, because you mentioned the tetrahedral shape of the carbon.
Yes.
Which ultimately then is the fingerprint of a diamond.
Yeah. So the tetrahedral shape. Basically, so your carbon atom is surrounded by four other carbon atoms. Okay, and usually the crystal structure and the structure of or the arrangements of atoms basically also determine the shape. So this is why you get, for example, these nice octahedral shapes determined through these little tetrahedrons.
Okay, why I asked that was because my thinking was this. You know, you talk about that new one that makes up 38% of the Earth. That and how, look, the further you go, then there's those very rare other creatures, and then there's the other stuff that gets to the top. So there's clearly this formation of carbon that is obviously washed and bathed and swims in this chemical soup below the surface and the layers of the Earth. And then you're seeing that beautiful ring of colors where you're saying, "Ooh, gee, it brushed across the boron," or "Ooh, it came into contact with a nitrogen." And then, so look, I'm not a chemist person. I'm a little techie keyboard jockey, but I've been to Kimberley. I spent a year there. It's very hot.
I know.
But at the Kimberley Hole, I saw that, and then obviously there is that that rush to the shininess, the light that you. It's almost so. Why I raised the question about the structure of this tetra structure was the 109.5 degree bond that exists in this tetrahedral structure. And so I was thinking, like, really, maybe at the center of the Earth, it's just like this huge carbon diamond. And you know, when you put the pyramid, when you put it has this magnetic property as well. So
sorry, sir. Unfortunately, our core is not made out of diamonds. That is unfortunately not the case.
What is it? Hot iron?
Yeah, it's nickel iron usually.
Okay.
So
doesn't it have a bit of? Can't you have those micro diamonds in it? So it is sprinkled or peppered with a little bit of diamond. It does have a bit of sparkle in us, surely.
I'm not actually sure. Maybe Jürgen can help us here. So how far does a diamond go down to, Jürgen? You only find it in the down to the lower mantle. Is that right?
Yes, yeah, because
Okay.
the core of the Earth, yeah, has basically no carbon at all, so you cannot have diamond there. It's
Okay, so
the composition of the Earth's core, and that's why it creates the magnetic field. That's all the iron there. Is completely different to the Earth's mantle. Okay, so what you find there is something completely different. And we know only about the Earth's core. Well, we know what the density is, and we can derive from that what it consists of. But the natural examples are iron meteorites that come from space, and they represent basically what we see in the Earth's core.
Yes.
Okay.
Yes. Okay, so the Earth is in fact a reflection maybe of these meteors that is it like a chemical store that just keeps spinning, and these bonds happen, and in this cooking soup in the core, things get burnt, turn into carbon, they get broken down into their, you know how you said, hey, when it comes into hydrogen, when carbon and hydrogen come under pressure and heat, then look at the door, look into the door, see how shiny it is. That's why I'm having a look at that door that you mentioned, the peak, the opportunity that we have. It's important because it's almost like looking at the periodic table and using an element, something like a diamond, to try and tell you the story, to solve the crime. The crime was the formation of the diamond. How did it happen? Yes, I'm following you in the way of, but I'm trying to, look, because I'm not a chemist person, and a geo person, but I know a diamond when it shines. I mean, you would.
Yeah, I know.
Thank you again, Tanya. That was a beautiful talk. I didn't mean to hijack your channel, but lovely.
No,
Thank you.
no, that's fine. That's fine,
Perfect.
sir.
Thank you, and thank you, Jürgen. Thanks.
No problem.
Maybe Jürgen, you can show the people here how the basically Jürgen has a kimberlite, and inside this kimberlite there's in fact a piece of a garnet that comes up. And maybe you want to show it to them.
Yeah.
Here we go.
Oh, sorry.
Oh, extra creamy. Here we go. The diamond. Is this my reward for giving this talk? That's great.
By the way, if you put chocolate under high pressure and temperature, you can make it a diamond also.
Ooh, here we go. Guys, you can try this out. Don't try this in the microwave, please.
Yeah, here's a piece of kimberlite, which just has a nice cut here, cut with a diamond saw on the one side. So you see how irregular the structure is. And this big cyclops eye here is a fat garnet, actually. Okay, that's why we took that piece. But what's surrounding it is pretty nondescript rock, which is actually the kimberlite, a volcanic rock. And it has all sorts of bits and pieces in there floating, single minerals, pieces of other rocks like peridotite, mantle rocks. And that's all what we find, these types of rocks and minerals in kimberlite pipes. And if we're lucky, we see the diamond. That comes from Monastery, which is the diamond bearing, one of the famous diamond bearing mines in South Africa.
Okay, thanks, Jürgen. Right, are there any questions, other questions? I can see there is not. Then I would say thank you very much for your attention. Thank you very much for joining us. And please don't forget, tomorrow evening we have our famous science show by Dr. Stephen Ashworth. And I'm really looking forward to it. He made an effort, so he's going to be live streaming from the UK, and I hope to see you back tomorrow evening. Okay, goodbye, bye-bye. Thank you so much for joining. Thank you. Bye.
Bye. Thank you.